I want to start by talking about the most common oxidation-reduction reactions. The first one we're going to talk about is combination. A combination reaction is one in which two or more substances combine to form a single product. As an example, I use aluminum plus bromine yields aluminum bromide, and you can see it's in a redox reaction because there is a transfer of electrons. I do want to point out that not all combination reactions are redox in nature, and the same holds for the next type of reaction, which is called the decomposition reaction. This type of reaction is the breakdown of a compound into two or more components. And as you can see, this shows 2 moles of potassium chlorate yields 2 moles of potassium chloride plus 3 moles of oxygen. And you can see by the numbers on the top, I've shown you which one gets oxidized and which one gets reduced. And a good thing to note is which one nothing happens to. For example, the potassium, if you notice, it stays with a +1 charge both on the product side and on the reactant side. Here I'm showing you another type of redox reaction. It's called a combustion reaction. Combustion reaction is one in which a substance reacts with oxygen, usually with the release of heat and light to produce a flame. The right picture shows sulfur burning air to form sulfur dioxide. And of course the bottom picture is magnesium burning in air to form magnesium oxide. You can see by the numbers on the top which one's getting oxidized and which element is getting reduced. Whereas decomposition and combination reactions don't all have to be redox reactions, combustion reactions do. So if you ever see a combustion reaction, it is a redox reaction. The next type of redox reaction are displacement reactions. There's 3 of them. The first one is hydrogen displacement. So in a displacement reaction, an ion or an atom in a compound is being replaced by an ion or an atom of another element. So in hydrogen displacement, all alkali metals and some alkaline earth metals, such as calcium, strontium, or barium, which are the most reactive of the metallic elements, will displace hydrogen from cold water. But for example, if I was to give you the bottom reaction, which says lead plus 2 moles of water, and this happens to be cold water, and then I show you those products, lead hydroxide plus hydrogen, which basically means that that hydrogen has been displaced by the lead, you know that this cannot happen. Because if you look at this table right over here, it shows that lead can only displace hydrogen if it's reacting with an acid. Since I told you specifically that lead is reacting with cold water, it is not able to displace that hydrogen. Only lithium, potassium, barium, calcium, and sodium are able to displace hydrogen by reacting with cold water. So you would use this table to figure out if hydrogen can be displaced. You do not have to memorize this table. This table would be given to you in a test if we were to ask you these questions. Another type of displacement reaction is the metal displacement. A metal in a compound can be displaced by another metal in the elemental state. So for example, here I have copper sulfate plus zinc will yield zinc sulfate plus copper. This reaction can happen because if you notice in the table, zinc is higher than copper. So that means that zinc has the ability, the reducing strength, to displace copper. So that's why that reaction happens. But if I was to flip this equation and say instead that zinc sulfate will react with copper, since copper is lower than zinc, it is not strong enough to reduce zinc sulfate. So that reaction does not happen. So again, you would use this table to help you figure out if the metal that's being displaced could actually be displaced. The last type of displacement reaction is the halogen displacement. Above I show you the activity series for the halogens. So for example, fluorine is a much stronger oxidizer than chlorine. Chlorine is a much stronger oxidizer than bromine, so on and so forth. So if I was to show you this reaction, chlorine reacting with 2 moles of potassium bromide, this reaction can happen because chlorine is a stronger oxidizer, therefore it can displace bromine. Now if I was to show you the bottom reaction, that reaction would not happen because iodine is not stronger than bromine, so it would not be able to displace bromine from that reaction. The last type of redox reaction I'm going to talk about is called the disproportionation reaction. We went over this in class briefly. Basically, it's a reaction where the same element is being simultaneously oxidized and reduced. For example, in the reaction below, chlorine is being oxidized and reduced. One thing to note is that the element that's being oxidized and reduced would be an element that can have at least 3 oxidation states. So chlorine can be part of a disproportionation reaction because it has more than 3 oxidation states, and nitrogen would also be something that could be in a disproportionation reaction. The next topic we're going to talk about is molarity. Molarity is a unit of concentration. The concentration of a solution is the amount of solute that's present in a given amount of solvent or a given amount of solution. There's many different types of ways to express concentration, but the most common is molarity, so we're going to deal with molarity. The definition of molarity is moles of solute per liter of solution, and it has a symbol capital M. A typical problem that you would see molarity in would be the following. How many grams of potassium dichromate are required to prepare 250 ml solution whose concentration is 2.16 molar? So the way you would tackle this problem is try to connect the different units. We know that molarity is moles of solute per liter of solution. So there's a unit of volume here, and we gave you another volume in the problem. So that would be a connection that you should make. So I would start with the 250 mils of solution. But since the definition of molarity is moles per liter, I'm going to go ahead and convert that milliliters to liters. So instead, I'm going to say 0.25 liters, and then I'm going to multiply that times the molarity that they give me. So it's 0.25 liters times 2.16 moles of solute, which it would be moles of potassium dichromate per liter of solution. So the liters cancel out. And they want how many grams of potassium dichromate, but I'm already in moles of dichromate, so the way that I would go from moles to grams is easy. This is a molar mass. So you would take the molar mass of potassium dichromate, which happens to be 294.2 grams per 1 mole of potassium dichromate, and then that's the unit that you need to be in. That's your answers, and you would multiply everybody out, and you see that you get 158.868 grams of potassium dichromate. The trick here, once again, is to try to make sense of the units. Write everything down and try to make connections. If you know that molarity is moles per liter and they give you a volume in the problem, then more than likely those two are going to have to be together somehow. And once you're in moles, then you can go from moles to any other unit that they ask you to. This particular problem asks us to go to grams. So it would take 158 grams of potassium dichromate to prepare a 250 ml solution whose concentration happens to be 2.16 molar. Next topic is dilution. So dilution is the procedure for preparing a less concentrated solution from a more concentrated solution. The equation for this is M1V1 equals M2V2, or like I have here, M initial times volume initial is equal to the final molarity times the final volume. One important thing to note is that you can only use this equation, N1V1 equals M2V2, if you're dealing with the same component. I can only give you information on one solution. Here's an example where you would use the dilution equation, M1V1 equals M2V2. The question reads, how would you prepare a 2.00 times 10 to the second milliliters of a 0.866 molar sodium hydroxide solution, starting with a 5.07 molar stock solution. So first thing is first, you have to realize that this is a dilution problem. So you're starting with a 5.07 molar stock solution and you want to dilute it to 0.866 molar. Another thing you need to know is usually when you see the word of, that means that the number before and the number after are probably going to be on the same side of the equation. Of is a symbol for multiplication. Keep that in mind. So what you're solving for is the milliliters, because you have everything else that you need. M1 would be the molarity of the first one, which would be 5.07 molar. Volume of the initial, you don't know, so that's what you're solving for. The final molarity is 0.866 molar, and the final volume is basically 200 milliliters. So all you would do is you would solve for X, and you see that it ends up being 34.2 milliliters. So the way you would make this solution is you would take 34.2 milliliters of a 5.07 molar solution and dilute it to 200 mils. That's how you use the M1V1, M2V2 equation. The last topic we're going to talk about is titrations. Acid-base titrations can be used in quantitative studies of acid-base neutralization reactions, and we know what those are. So in a titration, a solution of accurately known concentration, which is called a standard, right? That's the standard solution, is added gradually to another solution of unknown concentration until the chemical reaction between the two solutions is complete, or in other words, neutralized. So So basically, if we know the volumes of the standard and the unknown solutions that are used in this titration, along with the concentration of the standard, then we can basically figure out or calculate the concentration of the unknown, which is very, very helpful to us. So you will be responsible for learning how to do acid-base titration problems. This is actually not hard, and we know most of the steps already, but let's try a problem. A typical titration problem looks like this. In a titration experiment, a student finds that 23.48 milliliters of a sodium hydroxide solution are needed to neutralize 0.5468 grams of sulfuric acid. What is the concentration of the sodium hydroxide solution? So first thing you have to realize is that, yes, it's a titration because the problem tells you, but it's an acid-based titration because I'm telling you neutralizing. And another thing you should notice is that it's sulfuric acid, that's a strong acid, reacting with sodium hydroxide, that's a strong base. So when you get sodium hydroxide and sulfuric acid together, you're going to get a salt plus water. So the first thing you need to do is make a chemical reaction. Write it down. So sodium hydroxide plus sulfuric acid yields what? The salt would be sodium sulfate plus water, but this is not balanced. Okay, so you have to balance it. That ends up being 2 moles of NaOH plus H2SO4 yields 1 mole of sodium sulfate plus 2 moles of water. Now it's balanced. Now we can answer the question. Ask yourself, what is the goal? The goal is to find what is the concentration, so moles per liter, the concentration of the NaOH solution. So therefore, I am going to start with the other piece of information. So I start with 0.5468 grams of sulfuric acid. If you don't know what to do, what is usually the best place? Where is usually the best place to go? Go to moles. You have grams of sulfuric acid, go to moles of sulfuric acid. Once you go to moles of sulfuric acid, use the mole to mole ratio, just like we've done all through chapter 4 in the balanced equation. So you have 1 mole of sulfuric acid going to 2 moles of sodium hydroxide. Now you're in moles of sodium hydroxide. What is the question asking again? It's asking what is the concentration and molarity of sodium hydroxide. Well, guess what? You already are in moles of sodium hydroxide, so the only thing you would need to find the molarity is the volume, and they give you the volume. It's 23.48 milliliters, but for you to use that answer, which by the way was 0.01115 moles of sodium hydroxide, you have to make sure that you put the unit of volume to the correct unit. It's in milliliters, so you've got to change it to liters, which of course that would make it 0.02348 liters. So then you would divide the answer that you got into 0.02348 liters of solution, and that gives you 0.47492, so on and so forth. But since I have 4 sig figs, I'm going to keep it at 0.4749 molar. So in a titration experiment, a student finds that it takes 23.48 milliliters of an NaOH solution needed to neutralize that much of acid. What's the concentration of that NaOH solution? It happens to be 0.4749 molar. That is it for chapter 4. You need to practice very, very hard these problems. You are definitely going to have a titration problem, a dilution problem, and a concentration problem on your exam. So please concentrate on those. See you later.